Hello, everyone. Welcome to Physics 205. So this lecture is going to be on kinematics. Now, kinematics is defined to be the study of the motion of objects without consideration of the causes of the motion. So as you know, forces and torques will cause various motions. Well, kinematics doesn't consider forces and torques. We'll learn that later when we study dynamics or kinetics. So kinematics is simply the motion of the object. Okay, now there's several things I want to define here. The first definition is distance. So distance is defined as the total length traveled. Now, with distance, the direction that you travel is not important. It's just the magnitude, just the total length that's traveled. You can go back and forth and you have to keep adding those various intervals, okay? Displacement is defined to be the difference between the final and initial positions of an object. Displacement is actually a vector. It has both magnitude and direction. And again, it only depends on the initial and final positions of an object. So in general, let's say we represent the initial position of an object by r sub I, and notice here that it's a vector, and the final position by r sub f, then the displacement, which is written here as delta r, so it's another way of saying it is it's a change in position. So displacement is the same as change in position. So delta r, delta means change. It's defined to be rf, the final position, minus the initial position. So, and notice here that you're subtracting these two vectors and you're going to get another vector, right, which is the displacement. So in general, displacement is really a vector and it has both magnitude and direction. Now, a lot of what we're going to do in this class, we will look at this sum, but a lot of what we're going to do is look at one-dimensional motion. So for one-dimensional motion, the displacement, let's say in the x direction, would simply be the final position in the x direction minus the initial position in the x, and that will give you the displacement delta x, right? So again, that's the change in position, the displacement. This is simply be the x direction. And in this case, the sign of delta x, whether it's positive or negative, gives you the direction, right? Because if it's just one dimensional, then the vector is either pointing in the positive x direction or the negative x direction. And you can determine that from the sign of delta x here. Okay, so these are really vectors, but because it's just one dimensional, I don't even write the vector symbol. Okay, but in general, if you have 2 dimensions or 3 dimensions, then you have to write these as vectors. Okay, so let me stop for a second now, go to the iPad and show you some examples of this, of distance and displacement. Okay, so in this example, you're told that an individual starts in the center of town, walks 1 mile east, 2.5 miles west, and then 0.5 miles east. And we want to figure out 2 things. The first thing is we want to figure out the distance, the total distance that's walked, and then we want to figure out the displacement. Okay, so first thing I would do, let's draw a little picture here. Let's say the center of town is right at 0. I'll just draw, so it's one-dimensional, right? At 0 is the center of town. And then if we move to the right, these represent miles here, so 0, 1, and to the left would be negative. This would be -1, -2, -3. Okay, so the individual starts at 0, right? The center of the town here. They move, let's say, 1 mile east. So it's hard to draw it right on top of it, but I'll just kind of draw it next to it. So 1 mile east. And then they're going to move 2.5 miles west. So they turn around and they're going to go 2.5. So I guess they're going to stop there, right? Around -1.5 here. And then they go back 0.5 miles east. So they're going to end right there. Right? They're going to finish at that location. Okay, so to calculate, let's do distance first. So what is the total distance walked? Well, first, the individual is walking from 0 to 1, right? So that's 1 mile. Then they're walking from 1 all the way to negative 1.5. So that is another 2.5 miles. Again, remember, with distance, the direction doesn't matter. You're just adding the magnitudes. So 1 mile plus 2.5 miles. And then they're walking another 0.5 miles east. So I have to add another 0.5. And if you add all those values together, you're going to get an answer of 4 miles. Right? So the distance traveled is 4 miles. Okay, what about displacement? Well, remember, displacement is simply depends on the final position and the initial position. So remember, as a formula, and we're just talking about one direction here, right? You can think of this as the x-axis. So if I want to calculate displacement, that's delta x. That's going to be the final position minus the initial position. Well, the final position in this case, where did they finish? At -1 minus, and the initial position was at 0. So if I subtract those, -1 minus 0, I'm going to get -1 miles. Now, what that means is that the negative means that the displacement is to the left, right? In fact, if you want to draw it as a vector, we could draw it like this. Here's the initial, here's the final. So that would be the displacement as a vector. So the negative means it's pointing to the left, and its length is going to be 1, right? So -1 miles would be the displacement. Or another way of saying this, you could say it's 1 mile to the west. If you want to say it in words. Okay, here's another example. You're told that an individual rides a bike 2.5 miles east, then 1.5 miles north, then 4 miles west, and finally 2.5 miles south. And we want to compute the displacement of the individual. So we want to add up all these individual displacements to get the total displacement of the individual. And let's say we want, so this is going to be a vector, and let's say we want it in component form and polar form. All right, so again, I'm going to draw a picture here. So here's my, I'll just draw a coordinate system. And originally, the person is walking 2.5 miles east. So let's say they start right at the origin, right? So I'll call this like D1, displacement 1. It's 2.5 miles, and it's in the east direction. Then they walk 1.5 miles north. So that would be like this. And I'm just adding tip to tail. So I'll call this D2, 1.5 miles. And the direction is given by the vector, right? It's north. Then they walk 4 miles west. So again, I'm going to put the tail of D3 at the tip of D2. Draw it like this. So this is D3. And this is 4 miles. The direction is given by the vector. And then finally, 2.5 miles south. So I'll call this D4. And that's equal to 2.5 miles in south. Okay, so what I want to compute here is I want to compute the total displacement. So remember, if you look at this, right, the final position is right here, and the initial position is here. So I want to find the displacement, which is a vector that goes from the initial position to the final position. I'll call this delta R in this case. So that's the displacement. And I also want, so I want to figure out the magnitude, and I want to figure out this angle here, call it phi. Okay, So probably the easiest way to do this, if you notice, really to get delta R, what you're doing is you're adding up all those individual displacements. So delta R is going to be D1 plus D2 plus D3 plus D4. Okay, so I need to find, well, how do I do this? Well, I want to do this using components. So I need to find the X and Y components of each of those vectors and then add them all up, right? So in this case, it's a little bit easier though, because if you notice here, D1, it is pointing, that vector is pointing just to the right. So we know the X component, D1X, is simply going to be the entire magnitude and it's positive, right? 2.5 miles. And the Y component, D1Y, that's going to be 0. None of that vector is in the Y direction. It's all in the positive X direction. So actually, if I want, I can write D1 now as 2.5 I hat plus 0 J hat miles. Okay, D2. D2, let me stay here so I can see the picture. D2. So let's see, the X component of D2. Well, again, just by looking at this, I don't even need to do any trigonometry. It's pointing straight up, right? So there is no X component. So the X component is 0. The Y component, on the other hand, is going to be 1.5, and it's positive, right? Because it's pointing upward. So if I want, I can write D2 as 0 I hat plus 1.5 J hat miles. Okay, now D3, I'll do it over here. Well, D3X, it looks like it's pointing to the left, right? So it's all in the X direction, it's negative. So it looks like that's going to be -4 miles. And none of that vector is in the Y direction. So this will be 0 miles in the Y direction. So D3 is going to be -4 I hat plus 0 J hat miles. And then finally for D4, it looks like D4X is 0, but D4Y looks like it's negative. It's pointing down, so -2.5 miles. So that means D4 can be written as 0 I hat minus 2.5 J hat. Okay, so now to add these together, I have to add the X components, right? The I hats together, and then add the Y components, the J hats together. So my delta R here, remember, it's just going to be D1 plus D2 plus D3 plus D4. Oops, D4 here. Let me fix that. Okay, so this is going to be 2.5 I hat plus 0 J hat. And then D2 was 0 I hat plus 1.5 J hat. D3 was -4 I hat plus 0 J hat. And finally, D4 is 0 I hat minus 2.5 J hat. Okay, so if I add all the X components together, okay, so I just pick out the I hats here. I have 2.5 plus 0 minus 4 plus 0. That's going to be -1.5. So -1.5 I hat. And then if I add the Y components, right, the J hats, 0 plus 1.5 plus 0 minus 2.5, looks like that's going to be -1. So -1 J hat miles. So actually, that's my answer, right? In fact, if you look back at the picture, what it's saying is that the X component of delta R is negative 1.5, and the y component is negative 1, right? Negative 1.5, negative 1, and that's how we got delta r here. Now, ultimately, I want this to be in polar form, right? I want the magnitude of this vector, of this displacement, and the direction. Well, we know how to do that, right? From our study of vectors. How do I find the magnitude of this? Well, I need to use the Pythagorean theorem, right? So the magnitude of delta r is going to be the square root of the x component squared plus the y component squared. And if you do that, you're going to get around 1.8 miles. And then to figure out the angle, right? If you notice here, if I take this as my right triangle, then tan of theta is going to be opposite, right? Which was 1. The length is 1. It's negative 1, but the length is 1 over adjacent, and that length is 1.5. So in this case, tan of phi is equal to 1 divided by 1.5. So that means phi is going to be the inverse tangent. Remember, I need to take the inverse tan of both sides. If I take the inverse tangent of tan of phi, I get phi. That's what I want, the angle. And then to get this, I need to do this out on a calculator. And it turns out it's like 33.7 degrees. So, and I have to be a little careful, right? I'm in the third quadrant. So I could say something like south of west, and that would be fine. So the magnitude of that displacement is 1.8 miles, and the direction is 33.7 degrees south of west. Okay. Or if you really wanted to, you could add 180 to it, and you could give the direction from the positive x-axis, right, all the way to that vector. So it'd be 180 plus 33.7. Either way is fine. As long if you put south of west, though, that's fine. All right, great. Okay, so let's continue with some more definitions. So the next definition is something called the average speed. So the average speed is defined simply as the distance traveled, right? So it's distance divided by the elapsed time. So speed, or average speed, does not have a direction, right? It just has a magnitude, because remember, distance does not have a direction. So it's considered to be what we call a scalar. It's not a vector. It just has magnitude, but no direction. And mathematically, as an equation, it simply is defined as the distance, which I'm going to call d here, divided by time, which I'm going to call t. Okay, I'll show you an example in a minute. Let me just define what instantaneous speed is. So instantaneous speed is the speed of an object at an instant in time. Okay, we're going to see in a little bit too, it's also the magnitude of the velocity. Now, what's an example of this? Let's say you're driving on the highway and you look at your speedometer, right? What is that speedometer measuring? It's actually measuring the instantaneous speed. It's measuring the speed right at that instant. The instant that you look at it, that's your speed, okay? To compute the instantaneous speed, if you want to compute it exactly, this is somewhat complicated because it involves techniques from calculus. It involves computing something called the derivative, okay, which you're not expected to know calculus for this course. So in this course, if we wanted to approximate it, you can calculate the average speed over a very short time period. And that will be a pretty good estimate of the instantaneous speed. So in other words, you're just calculating the average speed, which we know how to do, distance divided by time, except we're making the time interval, the elapsed time, to be very, very short, a very short time period. Okay, and that will give you a pretty good estimate of the instantaneous speed. Okay, let me show you a couple of examples of that. Okay, so in this example, you're told a walker covers a distance of 2.2 kilometers in a time of 30 minutes. What is the average speed of the walker in kilometers per hour? And then we also want it in meters per second. So we're gonna have to do some conversions here. So first thing I would do is, since we want kilometers per hour and we have kilometers and minutes right now, let's convert 30 minutes to hours. So we'll do that conversion first. So if I start with 30 minutes, this will give you some practice on conversions again. We know that we want hours, right? We know the relationship between minutes and hours. We know that 1 hour is 60 minutes. So I'll put that on the denominator, so minutes cancels. And if you multiply that, you're going to get 30 over 60, which if you simplify is 1/2, right? So 30 minutes is exactly equal to 1/2 of an hour. So now to compute the average speed here, remember that's defined to be the distance over the elapsed time. So in this case, the distance is 2.2 kilometers, and the elapsed time is 1/2 of an hour. So if you divide those, right, you can, if you want, you could write this as 0.5. So half is the same as 0.5 hours. You're going to get 4.4 kilometers per hour. Okay, so that would be the average speed in units of kilometers per hour. All right, what if we want the average speed now in meters per second? Okay, so, well, first, let me convert my distance. I know my distance is 2.2 kilometers. Let me convert that to meters. Well, we know that there are 1,000 meters in 1 kilometer, right? Or you could also move the decimal point 3 places to the right. So if I multiply this, right, it's the same as moving the decimal point 3 places to the right. It's going to be 2200 meters. And then let's see, I want seconds. Well, and given the time, elapsed time is 30 minutes. So how do I convert that to seconds? Well, I know that 1 minute is 60 seconds. So I need to write it like that. So I guess I'm just multiplying 30 by 60, which is 1,800 seconds. Okay, so it's the same thing now. To find the average speed, I'm simply going to divide my distance divided by my elapsed time. But now I want my distance in meters, which I have, 2,200 meters. And I want my time in seconds, which is 1,800 seconds. And if you work that out, you're going to find it's 1.22 meters per second. Okay, so same thing, same exact problem, except just different units, right? Meters per second. Another way you could have done this is you could have just converted directly from this answer, from your 4.4 kilometers hours, you could just convert it to meters per second. And you would have gotten the same thing. We just kind of did it again by converting the distance and the time. Okay, let me do another example. Actually, this one on instantaneous speed. So in this case, you're told the position of a hit baseball was measured at 2 different times with a high-speed camera. Use the information in the table below, I'll draw out the table in a second, to estimate the instantaneous speed of the baseball at 1 second. Okay, so let's say in a table you have this. You have the position of the baseball. So position, this is say in meters, and then the time in seconds. So let's say the position of the baseball is 2.30 meters at 1 second. And then an instant later, right? Just a little bit of time later, it's at 3.33 meters. And that time was 1.001 seconds, right? So 1,000th of a second later, right? It's at a slightly different position, slightly further. And we want to estimate the instantaneous speed at 1 second. We'll notice here, right? So if I want to calculate speed again, I want the distance divided by time. And we said if we want to estimate the instantaneous speed, then we can do that as long as we have a really small time interval. In this case, the time interval to go from 1 second to 1.001 is really small. In fact, it's only 0.001 seconds, right? It's like a thousandth of a second. So if I take the distance, and what is the distance traveled? Well, the change in position here, it looks like is 0.03. So now if I take 0.03 and I divide that by the small elapsed time, 0.001, then that should give me, so this is meters per second, that should give me at least a pretty good estimate of the instantaneous speed at 1 second. And in this case, I'm going to get, if you divide that out, you're going to get 30 meters per second. So that's a good estimate of the instantaneous speed right at 1 second. Because I'm calculating it right around 1 second, and the time interval is very, very small. Okay, some more definitions. So the next definition is average velocity. So average velocity, again, it's a vector, and it's computed by dividing the displacement, which is a change in position, by the change in time, right? By the elapsed time. Since it's a vector, it has both magnitude and direction. In general, the equation is given by the following, right? Remember, it's the change in position. So if I take my final position of the object minus the initial position of the object, that's going to be the change in position, delta r. And I divide that by the final time minus the initial time, that's going to be the change in time. And the direction that this average velocity points in, remember, so it's a vector, it has direction, is going to be the same as the direction as the delta r, as the displacement here. Because the delta t does not have a direction, it's just a scalar, right? Just a number, it doesn't have a direction. The direction is incorporated into this change in position here. So the average velocity will have the same direction as the change in position, which is the displacement. Now, this is in general, right? If you have something in 2 dimensions or 3 dimensions, again, mostly we're going to be dealing with 1 dimension in this class. So 1-dimensional motion is a little bit simpler. So the formula simplifies to this. So there's a couple of ways I can write average. Sometimes I use v x av, meaning it's the velocity in the x direction and it's the average velocity. Some people will put a bar over the v to represent average velocity in the x direction. And that's simply going to be the final x position minus the initial x position over the final time minus the initial time. So in this case, it's just simply going to be delta x over delta t. And remember, delta x is either going to be positive or negative, so that tells you the direction, right? So the average velocity is either going to be positive or negative, and that'll tell you the direction. If it's positive, that means the object is moving in the positive x direction, right? Usually that's towards the right if we draw our axes like we normally do. So you could say forward or positive x direction. And if that velocity, the average velocity, is negative, then that means the object is moving in the negative x direction or backwards or to the left. Now, unfortunately, different books use different notation. Sometimes there's different notation even within a textbook. So sometimes instead of writing out like final and initial, sometimes I will use x naught, this 0 here means initial, and then x by itself to mean final. So like x naught and x would be the initial and final positions, and then t naught and t would be the initial and final times. So if that were the case, then the equation would just look slightly different. It would look like this. Instead of x final minus x initial, it'd simply be x minus x naught over t minus t naught. But it's still the same, the displacement, the change in the x position divided by the change in time. Okay, let me show you an example of this, of average velocity. Okay, so in this example, you're told an athlete swims the length of a 50-meter pool in 20 seconds and makes the return trip to the starting position in 22 seconds. And we want to determine her average velocity during the first half of the swim, during the second half of the swim, and then during the total round trip, the total swim. So what I would do, if, again, is draw a picture, right? So here, let's say this is the pool. And she's starting at 0, right? This is like 0 meters. You can think of this as like the x direction. And she's going first to the right to 50, right? So that would be like one length of the pool. And then the second, and again, it's hard to draw this because it's really on top, but I'm going to draw it right next to it. The second displacement is swimming back to the position, to the initial position, the starting position. Okay, so we want to calculate the average velocity over the first half of the swim, the second half of the swim, and then the total swim. So let me start with A, right? The first half of the swim. So first of all, remember the definition of average velocity. So Vx av is equal to the final position. I'll write it as xf right now, x minus x initial over tf minus t initial, which I can write as delta x over delta t. Okay, well, what is the final position for the first half? Well, that's going to be 50, right? xf is 50. The initial position is 0. She started at 0, the origin, divided by, and then the elapsed time for this first half of the swim was 20, right? 20 seconds. So then if I divide these, right, I have 50 divided by 20. That's going to be what, 2.5? So 2.5, I'll do 3 sig figs, meters per second. And notice that the positive is important, right? The positive 2.5 means that the average velocity was towards the right. So the vector is towards the right. And the magnitude is the 2.5 meters per second. But the direction is given by the sign, the fact that it's positive. Okay, second question. What is her average velocity the second half of the swim? Okay, so in this case, again, we still have delta x over delta t. But now, what is the final position? Well, she ends up at 0, right? Remember, that's the blue arrow here. Her final position is 0. Her initial position is 50. So now I need to do final position is 0 minus the initial position is 50 divided by, and in this case, I think it took, what, 22 seconds? So it's 22 seconds. These all really have 3 sig figs. Okay, so then if we work this out, again, the sign is important here. I'm going to get negative 50 divided by 22.0, and that's going to be negative 2.27. So this tells us that the average velocity was to the left, right? Pointing to the left, that's what the negative tells us. And the magnitude was 2.27 meters per second. So slightly slower on the second half of the swim. And then finally, to find the average velocity over the total swim, again, I need my delta x over delta t. Well, in this case, the final position is actually at 0, and the initial position is at 0, right? And the elapsed time would be the total time, which is what, 20 plus 22, so I guess 42 seconds. But what is 0 minus 0? That's simply 0, right? And then 0 divided by anything is going to equal 0. So it turns out that her average velocity over the entire time, the entire swim, is 0 meters per second. And why is that? Because her final position is at the same location as the initial position. And remember, average velocity only depends on that displacement. It's a change in position over change in time. So if the final and initial positions are the same as they are in this case, right? She starts at 0, ends at 0, then the average velocity is going to be 0. Okay, another example. You're told a student jogs once around a 200-meter track in 67.0 seconds. What was his average speed? What was his average velocity? So again, I'm going to draw a little picture here. Let's say, so let's say it's like it doesn't matter. Let's say it's like an oval track. So let's say this is a starting and ending position. It's an oval track. It looks something like this. And they're going to end back at the same spot here. Okay, so if I want to find the average speed, well, average speed is simply the distance traveled divided by the elapsed time. So in this case, the distance traveled is the total distance, right, around this track, which is 200 meters divided by the elapsed time, which is 67.0 seconds. So if I divide this out, it looks like it's going to be like 2.99 meters per second. So that would be the average speed, right? Just about 3 meters per second running around this track. But what about the average velocity? So average velocity. Well, in this case, right, remember that's the change in position. It really, in this case, I guess I'd have to do it as a vector over the change in time. Because this is really like two-dimensional. But notice here something. This initial position and final positions are exactly the same. I'll write that here. So initial position and final position are the same, are equal. So what is the change in position going to be if the initial and final position are equal? That's simply going to be 0, right? And then the elapsed time is 67 seconds. So again, the average velocity, because the person is starting and ending at the same position, it's going to be 0 meters per second. Okay, it seems weird at first, but it actually is 0, and it makes more sense if you think about it, because the velocity that they have at each of these is changing, right? The position is changing, and if you add up all those vectors, they're going to add to basically 0. Okay, so let me finish up by giving you a few more definitions, and then I'll go to the iPad again to do more examples. So we talked about average velocity. What is instantaneous velocity? Well, the instantaneous velocity is the velocity at an instant in time. Again, it's a vector. It has both magnitude and direction, but now it's simply calculated at some instant in time. To calculate the instantaneous velocity exactly, again, calculus would be needed. However, it can be estimated again by calculating the average velocity over a small time interval. Okay, and I'll show you an example of that in a minute. Average acceleration. The average acceleration is the rate at which velocity changes with respect to time. So remember how average velocity was the rate that the position changed with respect to time? Well, now this is like one step up. Average acceleration is the rate at which velocity changes with respect to time. Again, it's a vector quantity, and it's computed by dividing the change in velocity by the change in time. So in general, the equation is this. So it's a vector, right? AAV vector. It's equal to the final velocity, which is a vector, minus the initial velocity, which we can write that as the change in velocity, so delta V, over the final time minus the initial time, which I can write as delta T. So it's a change in velocity over change in time. And again, the direction of the average acceleration is given by the direction of the change in velocity, since this is the vector. Delta T is not a vector, it's just a scalar. So this is the vector. This gives you the information about the direction, the change in velocity. So that will be the same direction as your acceleration. Now, again, we're going to be mostly working in one dimension. So in one dimension, let's say along the x-axis, this equation simplifies a little bit. So now the average acceleration in the x direction is equal to the final velocity in the x direction, so just the x direction, minus the initial velocity in the x direction, which we can write as the change in velocity in the x direction divided by the change in time, right? Divided by the time interval. And again, the sign of this change in velocity will give you the sign of the average acceleration, right? So that gives you the direction. Since we're only talking about one dimension, the acceleration is either pointing to the right or pointing to the left. It's either positive or negative, okay? And that is found by the sign of the change in velocity. I'll show you some examples of that in a minute. And then finally, instantaneous acceleration is similar to what we've been talking about, right? It's the acceleration at an instant in time. Normally, you need calculus to compute it, but we could estimate it by computing the average acceleration just over a very small time interval, okay? And actually, also what I'll do when I do some of these examples is I'll show you examples of different directions of the acceleration. Like if the final speed is greater than the initial speed, what does that mean for the direction of the acceleration, right? So if I change the, I should really say velocity instead of speed. So if the final velocity is greater than the initial velocity, what does that tell us about the direction of the acceleration? If the final velocity is less than the initial velocity, what does that tell us about acceleration? So I'll go over some different examples of the direction of the acceleration. And it's really like 4 situations that come up. Okay, so having said that, let me go show you some examples of this. Okay, so this first example is an example of instantaneous velocity. So in this case, you're told a ball is rolling towards the left at 10 seconds, its position is negative 1.5 meters, and at 10.01 seconds, it's at negative 1.55 meters. And we want to estimate the ball's instantaneous velocity at 10 seconds. So again, remember to do that, we can calculate the average velocity in the x direction, right, which is defined as the change in x, change in position over change in time. Or if you want to write this out, you can say it's the final position minus the initial position over the final time minus the initial time. And as long as we have a small time interval, then that average will be a pretty good estimate of the instantaneous velocity. Okay, so in this case, actually, let me draw this out. Here's my coordinate system. 0, I guess everything is negative in this case, right? So like negative 1, negative 2. And initially, it looks like the object is at negative 1.5, and then a little bit of a time later, it's at this new position of negative 1.55 meters. These are both in meters here. Okay, so basically I can just plug in, right? My final position, it looks like, is the red, right? Negative 1.55. My initial position is at negative 1.5, right? So I have final minus initial divided by, and then the time interval is going to be, well, the final time was 10.01 minus the initial time is 10. So the time interval is just 0.01 seconds, which is a small time interval. So if you work this out, this is going to be equal to negative 0.05 divided by 0.01, which is equal to negative 5 meters per second. So that's a pretty good estimate of the instantaneous velocity, right? This object is moving to the left, that's what the negative tells you, and its magnitude is 5 meters per second. Okay, next example was on average acceleration. So in this case, you're told a car starting at rest accelerates to a velocity of 35 meters per second due east in a time of 12 seconds. What is the average acceleration of the car? Okay, so in this case, here, I'll draw a picture first. It's starting at rest. So you have this car starting at rest. And then 12 seconds later, it's moving to the right to the east. And its velocity is now 35 meters per second. So if I call this like final velocity, I'll just use Vx or final velocity is 35. And because it's at rest, the initial velocity V naught x is 0. And my elapsed time, my delta t, is going to be 12 seconds. So basically, I'm just plugging in, right? Remember, the average velocity, average acceleration in the x direction is simply going to be the final velocity in the x minus the initial velocity in x divided by the final time minus the initial time. So the final velocity is positive 35, right? Because it's moving to the right, minus the initial, so final velocity is 35 minus the initial velocity, which is 0. And then t final minus t initial is my delta t, that's 12. So it looks like in this case, this is going to be 2.92 meters per second squared. So that's my acceleration. Okay. Actually, be careful the units here, right? The velocity, the numerator is meters per second, and I'm dividing by seconds. So that's why I'm writing this as meters per second squared. You can think of this as, here, I'll do it out here. If you're dividing meters per second divided by seconds, I can put seconds over 1. You can think of these as like fractions. So remember how you divide fractions? You would take the first fraction, meters per second, and multiply by the reciprocal of the second one. So that's why we get meters, and on the denominator, we're left with seconds squared. So acceleration has units of meters per second squared. Now, what does this mean, the 2.92 meters per second squared, if that's the acceleration? It means that the car's velocity is changing by 2.92 meters per second every second. Okay, so you can interpret this. You could say the car's velocity is changing by 2.92 meters per second every 1 second, right? Every second. And because it's positive, we could say it's increasing by, so I'll say increasing by 2.92 meters per second per second. That's another way of saying it, right? If it was negative, then it'd be decreasing by that velocity every second. In this case, it's increasing. So this car is going faster and faster and faster, right? The average acceleration over that time interval is 2.92 meters per second squared. Okay, here's another example. A car is moving at negative 10.5 meters per second, and 5 seconds later, it's moving at negative 25.3 meters per second. What is the car's average acceleration over the 5 seconds? Again, we can just plug in, right? So we have AX av is going to be final velocity minus initial velocity over final time minus initial time. If we want, you can even write it like this, right? Final minus initial, and this is simply delta t. Okay, the numerator is delta v, but since I'm giving each one individually, I'll write it like that. So now if I plug in, what is my final velocity? Well, my final velocity is negative 25.3 minus my initial velocity, v naught x, is negative 10.5. And then my final time minus initial time, or my delta t, is 5 seconds. Right? It's over 5-second interval. So again, if you work this out, this is negative 14.8 divided by 5, which is going to be negative 2.96 meters per second. So in this case, the acceleration is negative, right? In this one-dimensional case, the acceleration is a vector pointing towards the left. So actually what's going on in this case is the object is speeding up to the left, because initially it was moving at negative 10.5 meters a second. So that negative tells you that it's moving to the left at 10.5 meters a second. And then the final case, it's moving at negative 25. So it's moving even faster to the left. So it's speeding up as it travels to the left. And the acceleration was negative 2.96 over that time interval. Okay, the last thing I want to do here is, actually it's similar to this problem right here. Given the initial and final velocities, I want to show you like the different possibilities for the direction of the acceleration. Okay, so I'm going to do this in pictures. So first picture. Let's say I have a car and it's traveling with some initial velocity to the right. And that arrow represents like the magnitude, and the direction is to the right. And then a little bit later, same car is traveling with a greater velocity, but to the right. So Vx. Okay, so I want to know what direction the acceleration is. It starts off with some velocity and it ends up with even a greater velocity pointing towards the right. Well, we know, right, the acceleration, which is really a vector. I want to write it in vector form now. So this is going to be like, so these are really vectors in this case, even though I'm just doing x direction, but I want to show you the subtraction of the vector. So this is going to be Vx final, right, minus V initial x divided by delta t. So the direction of this change in velocity, so this numerator here, which is a change in velocity, that's, since those are vectors, right, they have a direction, that change in velocity is going to give me the direction of the acceleration. The time, I'm just dividing by a time, there's no direction to time, so really the direction of the acceleration comes from the direction of this change in velocity. You could also write it like this. You could say change in velocity in the x over delta t. Right, so this, it's a vector. So that direction gives you the direction of the acceleration. Well, how do I subtract these vectors here? Well, we know how to do that. Right, remember, you start by drawing the first one. So V final x is like this. And then if I want to subtract V initial x, that means I want to add the opposite of V naught x. Right, so remember this subtraction is equivalent to taking Vx and adding the opposite of V naught x. And if V naught x looks like that, that means the opposite is going to be pointing in the opposite direction, right? So if I add tip to tail and I put V naught minus V naught x at the tip of Vx, it's going to look like this. And then if I draw a vector from the initial position, the initial Vx, to the final, to the tip of, basically from the tail of Vx to the tip of negative V naught x, it's going to look like this. So that's my delta Vx. But remember, that direction tells us the direction of the acceleration. So what it's saying in this case is that the acceleration is to the right. Okay, so if an object starts at some speed and it goes fast, if it's moving to the right and it goes faster to the right, then the acceleration is also towards the right. All right, let me do all the different cases. Let's say now that the object was initially moving, so this is like case 2. The car was initially moving really fast to the right. So v naught x. And then it slows down. Still going to the right, but slows down. So now if I want to find AF, then again, I need Vx minus V naught x over delta t. And the direction is going to come from that numerator, right? So if I start now with Vx, and I add negative V naught x, so now the tail of negative V naught x is going to go at the tip of Vx. So it's going to look like this. Then if I draw a vector from the tail of the first to the tip of the last one, it looks like that. So in this case, this is my change in velocity in the x direction. It's pointing to the left, which means my acceleration must be pointing to the left. So in this case, this car has an acceleration that's negative. Okay, so if you're moving fast to the right and slowing down, the acceleration is negative. Okay, here's another two more situations. Let's say now the car is initially moving to the left, at a small velocity, right? But it's negative, it's to the left. And then later it's moving to the left, but with a greater magnitude. And I want to figure out the direction of the acceleration in this case. Okay, so again, I'm going to use the fact that the acceleration is the change in velocity. It's Vx minus V naught x divided by delta t. So if I start with Vx, so that's just this Vx that I drew. And I want to add minus V naught x. So that's going to look something like this, right? If V naught x is going to the left, then minus V naught x is going to the right. And finally, if I draw a vector from the tail of the first to the tip of the last one, it looks like this. So that's my delta Vx. But that delta Vx has the same direction as the acceleration. So in this case, the acceleration must be to the left. Right? So these directions, that acceleration and then the delta Vx, they have to match the direction. So if a car is moving to the left and then speeding up to the left, the acceleration is to the left. And then finally, in the last example, let's say initially it's moving to the left again. But let's say it's moving fast to the left. And then it ends up moving still to the left, but much slower. So what is the acceleration, the direction of the acceleration in this case? So again, I'm going to find Vx minus V naught x divided by delta t. So I start by drawing Vx. I want to add negative V naught x to it. So now I'm going to put the tail of negative V naught x to the tip of Vx. So it's going to look like this, right? Because that's negative V naught x. And then finally, if I draw a vector from the tail of the first vector to the tip of the second one, it's going to be to the right here. That's going to be my delta V. But that tells us the direction of the acceleration. So in this case, the acceleration is to the right. So if a car, some object is moving to the left very quickly and it slows down, it's still moving to the left, but moving slower, that means you actually had an acceleration pointing to the right. That's what allowed it to slow down. Okay. This is a little tricky, especially when we're thinking about it just in terms of kinematics. Although I think it does make sense if you really understand the vectors, how the vectors add. This may make more sense when we talk about dynamics and kinetics in Newton's second law, because Newton's second law deals with forces and the acceleration, and that might be more helpful in determining the direction of the acceleration. But you should be able to get it just from the kinematics by looking at the change in the velocity vector. Okay, great. That's it for this lecture. Thanks.